Hello everyone, welcome back to the second part of lecture 8. So, we will continue this remote sensing data analysis with principal component analysis. So, before we start the principal component analysis and its application in remote sensing, let us understand the problems that we are facing in remote sensing data. When we talk about the remote sensing data, we have multiples of bands captured by sensor in different wavelengths. So, what happens? Remote sensing images are high in dimension and difficult to analyze. That means, when we talk about the dimension, that means here you have 1, 2, 3, 4, 5, 6 and 7 bands. So, these 7 bands have been used to capture or represent the information how it is behaving in different wavelengths, right. So, it can happen that some of the features, let us say this is the example of vegetation. So, some of the features are appearing multiples of time in different images, right. Let us say I have a sensor which is sensitive in these regions, right. So, if I refer to one particular object, let us say this is vegetation. So, this is second band, third band, fourth band, right. So, in this case, if you consider this is the reflectance of vegetation which is high in NIR, right. So, in this region you will not get any additional information or unique information for this vegetation, right, for this target. This is one of the example. So, if I have 3 bands, I will be having the similar information. So, these similar information what it will do? If you plot these 3 bands together or let us say 2 by 3, right. So, you will get the highly correlated information. This is the positive correlation. If this is like this, then it will be negative correlation, right. But even in both the cases, both the data sets are highly correlated. So, this is a big problem with remote sensing images because we try to gather more number of bands using different wavelength ranges. So, there is a chance that similar object will be captured in the image and they will have similar information in all 2, 3, 4 or 5 bands, right. So, even though it is very easy in multispectral to segregate this information, however, when we talk about the hyperspectral, it is a big challenge because there the number of bands are in the order of 200, 300 and the bands are very narrow and contiguous in nature. So, there the correlation will be much more than your multispectral data. So, in such situation what we have to do? We have to segregate or we have to identify the unique information which is available in 200 or 300 number of bands, right. So, that is why it is written remote sensing images are high in dimension and difficult to analyze. Acquired images are correlated, similar information in 2 or more number of bands to each other, right. In general, band acquired in different wavelengths are correlated. It is complicated to extract information about an object. Not all data sets are independent of each other. Now, let us take another example. Here you have 400 to 2500 nanometer. Now, one band which we are generating or the first image from that sensor is generated using 450 to 550 nanometer. Now, another one is using 1000 to 1200 nanometer, right. Another one is using 2300 to 2500 nanometer, and let us consider vegetation, right. So, here if you see, this is also capturing the green band, right. So, green is from 500 to 600 nanometer. So blue, green, red, remember 400 to 500 is blue, 500 to 600 is green, 600 to 700 nanometer is red wavelength. So this red wavelength is somewhere here. Now part of this green is coming into this, right. So if I redraw this, it will be like this. So in this 3 band, all the reflected portion of this vegetation is captured. So if I draw any one, first versus second or second versus third, because of this correlation, this will come as a positive correlation, right. But if I have a band here, let us say this is the second one, now this will become third and this will become fourth. In this case, what will happen? This second will not be correlated with 1, 2 or 4, right. Why? Because this is having different information about the target. So in this situation, band 2 is not correlated with 1, 3 and 4 band, but if I compare 1, 3 and 4, they are comparable and they are having similar information. So that is why we are saying all the data sets are not independent, whatever we generate through remote sensing. So we try to make this highly correlated data to uncorrelated. So if this is the data point, we will not have any correlation, right. So it says it is not dependent on this x or y axis, right. So if it is second band, if this is third band, in this case these two are not related. But if the data sets are like this, right, so we will see that we will have the high correlation. So we try to make this highly correlated information in such a way that it should become a uncorrelated data. So for that, what we have to do? We have to identify the inherent dimensionality of the data. That means the unique information which are present in the data will be identified and we will have a new set of images that will be used to identify the features. So the first problem is data redundancy and then second is the noise in the data. So these two will be a big problem or challenge associated with your remote sensing data. So we try to use this principal component analysis and we will be able to segregate the noise and to identify unique information in few number of bands or maybe equal number of bands depending upon your application, that we will try to understand in this particular lecture. Principal component analysis is a statistical method that uses orthogonal transformation. Orthogonal means perpendicular, right, to convert a set of data set into a set of values of linearly uncorrelated variables. So I hope you understood that remote sensing data captured in different wavelengths may be highly correlated because the similar object are having similar response in different wavelength region, right. The data reduction through correlation, that is possible. In general, band acquired in different wavelengths are correlated. Highlights or reduce the data redundancy. The number of output principal component images will be less than or equal to the number of input bands. Highlights specific features using their responses in different bands. Now, there are few terms which are coming again and again. So intentionally I have put them to make you understand that these are very important concepts. So you need to understand this data redundancy, why it is happening and what is the role of principal component here to reduce the data, and we should have the uncorrelated images, right. And with these images we can have the output which can be equal to the number of bands of the input, or it can be less than the input number of bands, right. And it can be used to highlight a specific feature that we will try to understand with feature oriented principal component. So, before that, first let us understand this PCA. So, this is the first case where we have this highly correlated data, and then what we do is we try to shift the origin from here to here, because this is a ellipse and here you will have the semi major and semi minor axis, and this axis will be shifted here, and with certain rotation what we will do, we will try to rotate and we will make it uncorrelated, right. So, how do we do that mathematically? That we will try to understand. So, for a data matrix X, which is nothing but the m into n, and it is a set of digital number, right. So, this size of the X is m into n, and the variance of an attribute can be calculated using this formula. This is the normal variance. How do we calculate the variance for two given parameter, right. So, remotely sensed images are high in dimension and difficult to analyze. Images are produced by sensors sensitive in different wavelength region. Images acquired are correlated and not all data sets are independent to each other. After variance, we have to calculate the covariance, right. So, the covariance of two attributes can be calculated using this formula, and now we have variance and covariance, right. Now, if I have this X matrix which is n samples and m measurement. So, here the size will become m into n, right, and what you assume here, all the measurements are not independent, right. So, we are assuming that our measurement is highly correlated. Principal component analysis is the eigen decomposition of the covariance matrix, which is nothing but the X transpose X, right. So, this is X transpose X that we have calculated in the previous slide. So, here we are going to do the eigen decomposition. So, this X transpose X, so the size will become m into m. So, the eigen decomposition will have two components. So, we will have eigenvector and then we will have eigenvalues, right, and we will be referring to these eigenvector and eigenvalues to generate our principal component images, right. So, here you can see this x dot w, right, is equal to t. So, w is the eigenvector or loading. In remote sensing, many times you will refer or you will notice that instead of eigenvector we are calling it loading, right, and t is the score, right. Each column of w is a principal component. Now, we will see the matrix how it is changing. So, this w is basically your eigenvector. So, the eigenvector column in the calculation will be your first principal component. Largest eigenvector column corresponding to the eigenvalue will be the first PC or the PC1, right. After calculating this, you have to order the column by the value of eigenvalues, right, because eigenvalue, high eigenvalue means you have more information in that particular column. Elements of eigenvector matrix columns are weightage assigned to the input bands of the PCs. Once the data is transformed and ordered, PCs can be selected to represent the unique measurement. We will try to understand this in that table. So, before that, when we are having this W and here W1 is your PC1, PC2, PC3 like that, PCR. So, principal component corresponding to the largest eigenvalue is the first one. So, here you have the highest eigenvalues. PC1 will have the eigenvalue. So, the truncated WR can be formed when first R column. So, as I discussed, this output can be controlled and here the output can be less than the number of bands provided in the calculation. So, this WR can be introduced. So, the R can be less than or equal to the number of bands. So, depending upon that R, and after you have sorted this table with this eigenvalues. So, the W1 is having the highest eigenvalue. So, like that first, second, third, fourth, like that, and the R, the first R will be considered and the rest will be discarded, right. So, the R column which contains maximum information will be in your output data. The expression will become like this. There is a two-dimensional data where m is equal to 2. So, here this data is highly correlated, right. So, the first eigenvector Wi of W will have maximum variance, that means lambda, right. Here lambda we are referring to variance, and here after the principal component analysis, this W1 will become the less correlated or uncorrelated. Finally, we will have this kind of table where you can see all the bands are listed here. Now, here you have W1, W2, W3, W4, W5 and W6. So, this is your output, right, and this is your input. So, we have used the Landsat data. So, the first, second, third, fourth, fifth and seventh band of Landsat 7 that was used here, and this is the W1, this is eigenvector, right, and this is the variance. So, this is eigenvalues. So, you see this table has been sorted based on this variance. So, now the first column which refers to this eigenvector first W1, here you have this PC1, right. So, the first element of this table which is a loading, right. So, this is also a eigenvector, and earlier I referred eigenvector, we will be referring it to the loading, that means it is the weightage to band number 1, right. So, when we talk about this 0.22, this is the weightage for band number 1, this is the weightage for band number 2, this is the weightage for band number 3, like that we will have the weightage for all the bands. So, if I have to produce principal component 1, what will be the expression? So, 0.22 multiplied with band 1 plus 0.37 multiplied with band 2 plus 0.69 multiplied with band 3 plus 0.38 multiplied with band number 4 plus 0.42 multiplied with band 5 plus 0.12 multiplied with band 7. So, if we do this calculation, we will have the principal component 1, right. So, this is how the output is generated using the principal component analysis, right. So, this is the input band. Now, here we are taking the same Landsat 7 data. So, the band 1 is basically your blue band. Here you see this information is like this. This is green wavelength. You see how images are different when they are captured in different wavelength, right. So, this is red, earlier was green, then you have NIR. Now, you see in NIR the brighter pixel, remember the vegetation, right. So, here you will find more brighter pixel which are from the vegetation, right. This is SWIR, this is again SWIR, and this is the false color composite. I hope you remember the false color composite. How do we generate? So, this is just a mapping, right. We have 3 guns in our display system, and then we are trying to put different combination here, and then we are generating the color composite. So, this false color composite is used, that combination, to display this particular image. So, here all the red colors are basically your vegetation. Finally, after the principal component analysis, we have this table, and this table will provide you all the necessary information to generate the principal components, right, because you have the inputs. Now, this is the output, principal component 1, this is principal component 2, principal component 3, principal component 4. So, here we have truncated it, let's say we don't have these two columns. So you remember the WR. So here we have given WR is equal to 4. So the first 4 columns will be used to generate your output, right. So in this case we have all these principal components. So this PC6, that means here you have 6 output and 6 input, that means both are equal. So we have not introduced any threshold here. Depending upon your application, you have to select which particular principal component is suitable, right, or will be providing you the information. So here let's say one example, this is PC6. So all these weightages are used here, right, and this corresponding bands, and then PC6 is generated, right. Now we will talk about the feature oriented principal component analysis, because now we have understood how we decorrelate the data, how we identify the inherent dimensionality of the data, right, and then we try to identify features or the target with this method, which is called feature oriented principal component analysis. It is also known as CROSTA technique, right. So that we will discuss now. To understand this feature oriented principal component analysis, let us take the example of the previous slide. This is the table. Now we will consider this Landsat 7 ETM plus, right, which is used to generate this particular table, right. Now here this particular figure is used to explain or demonstrate how gypsum spectra is behaving between this 400 to 2500 nanometer, right. Now you see it is having several absorption feature in different wavelengths, right. So these are the characteristic wavelengths, if you remember. So if I have to identify gypsum using this principal component analysis, then we have to refer this feature oriented principal component analysis, which is known as CROSTA technique. Now this gypsum and these, you can see, I hope this is clear. So here these are the wavelengths which are used to generate first band, second band, third band, fourth band, fifth band and seventh band, right. So now here the distribution of this gypsum. So here first, second, third, fourth, all these bands are having the only reflected energies, right. But if you see this band 5, it is having the peak which is getting captured, and fortunately Landsat 7's fifth band is capturing this particular phenomena, right. We would have been very lucky if we would have got this particular absorption feature in one of the image, but that is not available. So now we will rely on the other information which is captured in band number 7, right. I hope this is clear. So now we have two different bands which are of our interest when we talk about the gypsum. So this is band 7 and this is band 5. Now we will go back to this particular table where we have the loadings, right. So these are the loadings or the weightage, or this is the eigenvector value, right. So this eigenvector we will refer and we will try to find which of the principal component is having very contrast loading of band 5 and band 7, right. So if I refer to this band W1 or the PC1, the band 1, band 2, band 3, band 4, band 5, band 7, all are having almost similar loading. Band 3 is having the maximum, but almost they are having the positive loading, that means the positive weightage, right. When we talk about the principal component 2, here the band 3 is having the lowest one, but band 5 is also having lowest. So our interest is to find out this negative or positive loading of band 7 and band 5, where all other bands are having some different combinations so that these two can be easily identified, right. So now we will go back to this table and we will refer to this third column, which is PC3. Here also you see the values are in the same range, right. These 3 are negative, but these 3 are positive. So it is very difficult to differentiate between this band 4, band 5, band 7. Then band 4 or the PC4, that is also having the similar nature. But when we come to this PC6, right, here you see this band 1 is having 0.1 weightage, band 2 is having minus 0.05, band 3 is minus 0.05, which is these 3 bands, right. Then band 4 is having 0.03, this is also fine, but here band 7 is having the very high loading, which is for this particular absorption feature. Now for band 5 it is minus 0.24, that means it is having the maximum negative loading for the band 5 and maximum positive loading for band 7. So we have got a combination where we have got these two, absorption and the reflectance peak, and if we can use them together, then we will be able to separate this gypsum pixel from the other pixel of the image, right. So here what we will do, we will go with this band 5, band 7, and the characteristic absorption feature of this gypsum is 1700, 2210, 2440 nanometer, right. So here we have used this 2440, right. So here we have used this particular absorption feature so that we can identify. So we can generate this principal component 6. Now my question is, since we have got this band 7 very high loading, right. So this high loading means the pixel will be bright or dark. Since we are having high loading, this will be bright, right, and this is minus 0.24. Now see this clearly, when you are having band 7 very high loading, and band 7 is the absorption feature of this gypsum, right. So this is dark pixel in the image because this value is not available, this is absorbed, all other values will be high. So in this particular image, this absorption feature will be represented by the darker pixel, right, and when you are having high loading of this darker pixel, right, in the output of principal component, this is PC6, all the pixels which are dark, that will be representing your gypsum, right. Similarly here you have used the different combination, or here we have also got the positive loading for this band 5. Since we have got the negative loading for band 5, which is 0.24, and here we have this 0.96, this combination will provide you darker pixel in the principal component 6, right. So in your output you will be able to easily identify gypsum pixel using this feature oriented principal component analysis, right. With feature oriented principal component analysis, I will end the lecture 8 and will continue this course with lecture 9 in the subsequent or upcoming videos. Thank you.